So they were, it is a week 3 recap. We studied about equilibrium and kinetics, application of all those things in the reactor. We also studied about reversible and irreversible reaction in reactors, and we there was some concept about acids and bases. Further, this was from the week 2. We also studied about how to solve systems at equilibrium. We can go for mass balance, so there will be a system of equation, and how to solve them either through mass balance, charge balance, equilibrium equation, and component balance. So we studied component balance in the last session. And what are the reaction kinetics? It can be either reversible reaction or irreversible reaction. The reactions are kinetically controlled, and for irreversible reaction, equilibrium constants are higher. So I explained all those things in the last session as well. We also studied about rate of reaction. So it depends upon the concentration of reactant. When we talk about equilibrium, it depends upon concentration of reactant and product both. But when we talk about rate of reaction, it depends upon the concentration of reactant in any direction. And temperature for a particular reactions is optimum, has a highest rate at a particular temperature. If the temperature increases or decreases, the rate of reaction may change. In most of the cases, rate increases with the increase in temperature, but in some concepts, the reactant may reduce. The rate may reduce. This also depends upon stoichiometry. So it is a relationship between rate of different components with the rate of reaction. And these are different equations for your reference. So batch reactor, it is a completely mixed closed reactor. And if we take this example of A is going to 2B, so rate of reaction DC, this C means the concentration of any either A or B. Okay, it is equal to rate of forward direction reaction minus rate of backward. So what will be the concentration of Ca in batch reactor? Ca is equal to C naught A e raised to power minus kT. Okay, so this is the equation for the reactant. Okay, because something is reducing, that is why we have minus sign here. If it is increasing, then we can have plus sign. Okay, so Ca is equal to Ca naught e raised to power minus kT. It can also be written as, if we want to write it in terms of B, it can also be written as Ca is equal to Cb naught plus 2 Ca naught 1 minus e raised to power minus kT. So Sir has explained how this is taken forward. All this derivation was explained earlier. Second kind of reactor is completely stirred tank reactor. So it is also completely mixed. Okay, but it is not closed. So difference between batch reactor and CSTR is, one, batch reactor is closed because once if we are adding anything, we are not changing it. But in case of completely stirred tank reactor, we can, at one space we can add, and from other space we can remove. So if this kind of reactor are there, it is called completely stirred tank reactor, and it is continuously mixed. Okay, there will be stirring and it will be completely mixed. So this is CSTR. And if A is changing to 2B, what is happening? C out minus C in by theta. Theta is HRT, hydraulic retention time, is equal to RF minus RL. Ca is equal to Ca naught 1 plus K theta. And theta can also be written as V by Q. V means volume and Q means flow rate. Let's say if this is in liter, volume of the reactor, okay, volume of the reactor, and Q is flow rate. So it can be liters per second, maybe any unit you can take, liters per second. So When we will divide the units, what we will get? We will get second. L divided by, I'll write here, L, that is in liters, divided by L by S. We will get L will cancel and we will get S. So unit of HRT, that is hydraulic retention time, is second. So unit of this will be second. And what will be CB naught? Here it will be CB actually. CB is equal to CB naught minus 2CA naught K theta upon 1 plus K theta. And theta is HRT. And when we talk about plug flow reactor, here the concentration changes with distance. Okay, if A is changing to 2B, then dC by d theta will equal to Rf minus Rr. Here also theta is V by Q. Ca is equal to, the equation will be very similar to batch reactor, because here it is changing with distance. So Ca is equal to Ca naught E minus K theta. Here it will be simple time. Time is 1 minute, 2 minutes, like that. If we are taking a reactor, we are measuring at time t is equal to 0. There will be some value. If we are measuring at time t is equal to 5, it will be some value. But here, there is difference between theta and time. Okay, time is what you see in a clock. Okay, t is clock time. Okay, it depends upon the clock. Okay, but theta is hydraulic retention time. It depends upon volume and flow. Volume can be fixed. Okay, for this reactor, if we say volume is 1 meter cube, so it will be 1 meter cube only. But the Q may vary. Flow can vary. So theta is not clock time. It is the time of V divided by Q. So this is the difference between this T and this theta here. So that is the difference between batch reactor and plug flow reactor. Okay, even though equations are same, the sense of theta and T are two different things. So what is the relevance of acid-base reaction? Why do we want to study the acid-base reaction? So first is neutralization before biological treatment. For example, if there is a pollutant here and I want to degrade it using bacteria, but let's say if this bacteria will be most active at pH 7, but this bacteria will be optimized as pH 7, but the pH of this system is, let's say, 3. It is very acidic. It contains a certain pollutant and this bacteria is active at pH 7. So we need to do some acid-base reaction. We need to add some bases to increase the pH to 7. So from where we will get how much bases do we need to add? From the acid-base reaction. Secondly, avoid corrosion of distribution pipes. So if some acidic water is coming in a pipe, what will happen? It will be corroded. Okay, there will be formation of pits, there can be holes also. From the water may leak. So to reduce that, we need to maintain the pH of the water flowing through those pipes. For that purpose also, we need acid-base reaction. Okay. A pH during heavy metal removal or coagulation and flocculation. The heavy metals, okay, so there is some concept called solubility. And this is pH in the z-axis, x-axis. What happens? Heavy metals are there, they have a certain minimum solubility at a certain pH. So there will be certain pH where the solubility is minimum. So when the solubility is minimum, what will happen? It will no more be dissolved in water. It is going to come out in the form of precipitate. Any heavy metal, any target heavy metal we want to remove, it will come out as precipitate. So that is our target. So for doing that, either we need to add bases or acid. For example, if the pH is 7, we know if the pH of the water is 7, and we know that at pH maybe 5, something will precipitate. So we will add some acid. And if something will precipitate as pH 10, we will add some base. So for that purpose, we need to know the pH, acid-base reactions. For the acid rain on a particular lake. Normal, the pH of rain is 6.5. The rain that falls from the sky is never pH 7. It is pure water, but pH is around 6.5 because of carbonic acid, because of CO2. CO2 produces carbonic acid. Because of that, normal pH is 6.5. But sometimes this pH can go up to 5. When the pH becomes 5, we call that rain as acid rain. Okay. Above 5, we do not term it as acid rain, even though the pH is in acidic range. But that is not problematic. But when the pH reduces to 5, then we start calling rain as acid rain. Okay. So, if there is acid rain on a particular lake, the flora and fauna of that particular lake will change. So to maintain that, we need to study this acid-base reactions. Also, sometimes there may be cases where we want to know the pH after mixing of waste from different sources. Some pollution is coming, here the pH is 3, and some other source it is coming, the pH is 12. And they are mixing together. So what is the pH of this particular lake or water body or whatever stream? We need to know the pH. So for that also. And interaction of soil and water regarding groundwater contamination. The soil and water may interact and may allow some pollutant to go seep into the groundwater. For example, heavy metal also. If the pH is sufficiently high, okay, if the pH is in solubility range, what will happen? Heavy metal will be dissolved in water, and then via soil it may go down to the groundwater after rain. So we do not want that. So that is why sometimes we maintain the pH of the soil so that the solubility of these heavy metal or any substance can reduce. So this is why we need to know the acid-base reactions. Next concept is there are two ways in which we can define acid and bases. One is Bronsted-Lowry, another is Lewis. So when we talk about Bronsted-Lowry concept, so it is applicable to only aqueous solution. Okay, only when something is dissolved in water it is applicable. And proton donor, H plus donor or proton donor are called acids, and with the substance which accepts H plus or proton is called base. So this is Bronsted-Lowry concept. And it is only and only applicable to the aqueous solution. And when we talk about Lewis acid, so it is applicable to both first aqueous and non-aqueous solution both. So that is one important thing, and it is kind of a broader perspective. It is applicable to both aqueous and non-aqueous. And here acid is the substance, the compound that accepts non-bonding electron pair. So they are called acid, and which donates non-bonding electron pair is called base. Please note it down. This will be the important concept and important slide for you all. So Bronsted-Lowry is only applicable to aqueous solution. So it has lesser applicability. But the Lewis acid and bases, they have more applicability. Their scope is more because they are applicable to both aqueous and non-aqueous solution. It's not like that only something which can be dissolved in water will be making it acid or base. Sometimes it can be dissolved in non-aqueous solutions also, benzene or other solvents. So that is why Lewis acid has more applicability. So for acid-base reaction, what is important? Kinetics or equilibrium? So sometimes when as soon as we take 1 ml of some acid, HCl let's say, and we dissolve it in water, within a second it will react within a second, even in less than a second. And if we touch the surface, it will be very hot. Okay, if we are dissolving acid in water. So that is first exothermic reaction. And the temperature, it's not like the temperature will gradually increase. Temperature will just increase. So the reaction is very fast. So kinetics is not important in case of acid-base reactions. Okay, what is important here? Equilibrium. So how far the reaction is going is more important than how fast the reaction is going. Okay. Apart from that, if there is some Ha means acid and it dissociates into H plus and A minus. So H plus and A negative are called conjugate acid base pair. So this is acid, this will be conjugate base. And Henderson-Hasselbalch equation, it is used for preparing the buffer solutions. Okay, so why do we study this equation and Henderson-Hasselbalch equation? To prepare, one application is to prepare buffer solutions. And what are buffer solution? We'll study in a while. Okay, the solutions for which the pH will not suddenly change. There will be, it will resist the change in pH. Those are called the buffer solution. And pH is equal to pKa plus A minus means conjugate base upon conjugate acid. So this is called Henderson-Hasselbalch equation. Please note this down. It will help you in solving today's question. So coming to question number 1, match the following. Okay, you need to match the following concepts and we'll see the solution in a while. Please do this question. You can answer in the chat box once you are done. Okay, we'll see the solution. The solution is option B. So this volume dc by dt is the mass accumulated. Okay, while solving batch the reactor problem, we were writing something no before equal to. So that is accumulation is equal to incoming minus outgoing, right? So how do we calculate it? How do we mention this accumulation? Incoming flow minus outgoing flow, which is represented by V dc by dt. Second is QI CI. So these are all coming from the reactor kinetics, reactor analysis. So QICI is mass flow rate coming in because of I we can say that, and Q naught in I is incoming and O is outgoing. Okay, and this V RF minus RL mass formed or consumed. Okay, so for any kind of reactor this is applicable. And when we say reactor is in steady state, then this will become zero. Simple. But normally, this is the first equation that we write for anything. V dc by dt is equal to incoming minus outgoing plus or minus reaction. Okay, this is what we write. And when we say student steady state, simply this side will become zero. So this is how we were solving all the reactor analysis problems. Okay, then yeah, this is what I already explained. So the following data provided is relevant for the next two questions. Question number 2 and question number 3. A carcinogenic compound X present in water undergoes decomposition in a completely mixed flow reactor. So this is second kind of reactor. To a simpler compound Y as given below. X is being converted to Y. Inflow water flows at the rate of 2 meter cube per day. So Qi is given. The volume of the tank is 500. V is given. The raw water contain carcinogenic compound X and compound Y with the concentration of 500 to 10, so 500 and 10 respectively. So for one compound, it is Ci is given, and for the other compound also Ci is given. Assume rate constant to be 4 per day. K is given, okay, and X is equal to zero point 0.5 into molar mass of compound Y. So you note this down, then we'll see the question. You note down all the relevant points. QI, CI1, CI2, everything. Note this down. Okay, we'll see the question now. So what will be the concentration of compound X in the effluent? So what was X? X is changing to 1.5 pi. So X is reactant here. So what is the concentration of compound X in the effluent? Effluent means outgoing flow. Okay, please solve this question. Okay, I hope you are done. Match it with your own solution. So Q in, we know 2 meter cube per day. Okay, inflow was given, right? I'll show you. 2 meter 2 meter cube per day was inflow. Volume is 500. Okay, and 510 were there. So Q in is 2 meter cube per day. K is given 4 per day. C of X naught is 500 milligram per liter and Cy naught 10 milligram per liter. V is 500 liter and we know that it is given in meter cube. So we will homogenize the unit. So it is done in meter cube. Theta is equal to zero point 0.5 divided by 2. I told you, right? V by Q. So V divided by Q, we got theta. Since it is completely mixed flow reactor, C is equal to C naught by 1 plus K theta. Okay, in this question we are talking about just Yx. Okay? So later you can calculate Y for your own, but here we are calculating just X. So be very careful when this question comes in exam, because when they are asking X, then you have to specifically mention X. C naught is equal upon 1 plus K theta. Simply you are putting and you will get the result. Okay, note this down. We'll move forward to the next one. Coming to next question, what will be the concentration of compound Y in CSTR after 3 hours? Okay, 3 hours is given. Please do this question, solve this one. Solve this question. You can answer in the chat box when you are done. and then you can match with the solutions that I'll show. Okay, so as I told that since it was given in hours, we need to convert it into day. So that is why 3 divided by 24 is equal to 0.125 day. And Cx is equal to Cx not 1 plus k theta. Okay, Cx we can calculate, and similarly we can calculate Cb after 3 hours because the rate of reaction will be similar. So Cx naught minus Cx upon the stoichiometric coefficient we know. Okay, that was given 1 and 1.5, right? And Cy minus Cy naught upon theta y. Okay, and similarly we can simply solve. You note this down, then we'll see the further solution. Okay, further just keeping all the values, we can get the value of Cy. So from Cx we can get the value of Cy. I'll show the question and the solution again. So this was the data. We have Q value, we have V. Okay, we had know that in the X and Y both are reactant here. Okay, and X is being converted to Y. And the concentration of reactant, that is C naught X, is 500 and C naught Y is 10 milligram per liter. K value is given 4 per day, and compound X is equal to point like X by Y in molar mass is equal to 0.5. Okay. So the question was, what will be the concentration of compound Y in CSTR after 3 hours? So we can calculate X first. X is simple, Cx after 3 hours, we got the answer. Cx is equal to 333.333 milligram per liter. Now we from Cx we need to calculate Cy. So simple stoichiometry we can use. Both sides it will be equal. Okay. Then just by equating we got the answer. We know the initial values. Okay. Cx not minus here in reactant side. In reactant side initial minus final, and in product side final minus initial, or we can put a minus sign here. Okay, if both side we are putting the reactant initial minus final, then here we can put minus side because x is being converted to y, right? So something is producing and something is being used, so other side it should be minus a, we are putting the same, but here we are putting cy minus c naught, so just opposite of this, so minus is included inside. So that is how we'll get this. And we know x by y, that was zero point 0.5, x is equal to 0.5 y, right? So we are putting values of this and simply we can solve, and by solving we will get Cy is equal to 510 milligrams per liter. Moving forward, a reversible reaction follows below process in a batch reactor. A is changing to B and it is a reversible reaction. Please remember, it is a reversible reaction. The rate constant for forward reaction is 0.5 and backward is 0.8. So backward reaction is faster. Initial concentration of compound A and B are 250 and 150. Assume that the molar mass of compound A and B is 50 gram per mole and 30 gram per mole. What will be the concentration of compound A at equilibrium? Okay, it is a numerical based question. Here you have to give an answer. In a particular range of answer, your answer will be considered correct. So you have to round off to 2 decimal places. There in this kind of question, there will be no marks. We know the rate of forward reaction and rate of backward reaction. We know their molar mass and we know the initial concentration. We need to find out the concentration of compound A at equilibrium. For your own goodness, you can find out the concentration of B also. So for now, for this purpose of this question, please find out the concentration of A. Please solve this question. I'll give you 5 minutes to do so. We'll see the solution. So it is very simple. CA is equal to rate of backward reaction, CA naught plus CB divided by rate of backward reaction plus forward reaction, like in denominator. Simple. You can derive this also. It was properly derived in the class, so I'm not giving the derivation here. So simply you can use this formula and solve the question. Coming to the next question, the following data were obtained in a batch reactor in which containment is being removed. Okay, it is a batch reactor. At here, T is clock time, as I told earlier. Okay, so concentration and time are given. Calculate the fractional order n for the reaction using R is equal to Kcn. Here we need to use regression analysis. Okay, you can solve this in Excel also. Please note this down and try to solve. So the here answer is 1. Please note this, match it with yours, and then we'll see how solution, how it is 1. So first we need to assume an initial value. Let's say k is zero point 0.5 and n is equal to 2. We have time and concentration. We have time and concentration. We can find out dc by dt. Simple. How we can find dc by dt? Simple. C naught minus, like 400 minus 450. 400 minus 450 divided by whatever time is here, 1 minus 0. So we get minus 50. Like that, we can find out others. And when dc by dt is this rate, we are just putting, we are removing the minus sign, and this will be the rate. Okay. And by using the model, what is our rate? This is the rate by using model. What is our model? Model is R is equal to KCN. Okay. K is zero point 0.5, C is 2, C is this value, and N. So model rate is 0 0.5 into C, like for C, if it is 450, into N. N is 2. Okay. We can find KCN and we will get the values. Okay. We can calculate the error between them and squaring of error. This is the, now our target is to reduce this sum of errors. Okay, this is our target. So by using solver function in Excel, so there is a function called solver in Excel. By using that, we can change the target value of k and n and reduce the error. So when we reduce the error, we found these values. K is 0.49 and is equal to 0.73. So that will be our correct answer. Okay. The important thing is this value that is here is not is equal to 44.82. Okay, this will be equal to 450 only. So initially, maybe I can solve this question for you. That will be better. I'll show you how to solve this question. time and concentration. Serum. Serum. Okay. Fine. And the concentration is 450, 400, 277, 212, 149, 111, 63, 15, and 5. Now we can calculate the rate. The rate, as I told you, this subtracting this divided by this minus this. So this is rate, and rate without the minus sign, or we can keep the minus sign, no problem, we will solve it. And now we need to find out the rate model, that was KCN, right? So our K value and C and N value, let us assume K is 0.5, you can take anything, and N is 2. Okay, now we will use the KCN value. So what was K? K into C into N. Now here important thing is, these values, okay, we need to fix them so that they won't change. Okay, and here also we need to fix it. This is the modeled value. We need to calculate error. Square of error, let's directly calculate, is equal to this minus this raised to power 2. Okay, now we will get the sum. Now we need to use the solver. This is the solver function. We will use this. Our target is this cell. Okay, our target is this cell. Now we need to minimize it. And what are the variable cell that we need to change? This. Okay, everything will keep same and we'll solve it. Okay, there is some issue coming. Okay, maybe we'll change the rates, because the thing is, if we are not giving the correct values, if we are not giving the initial values correct, then it won't be able to solve it. It will not conserve the correct values. Maybe we can give some constraints. We'll see what can be done. Okay, C1 is fine. It has not changed the values. We'll see. Just a second. Sometimes it will give some erotic result. What I have done earlier is create this. Because here it is there is no value, so there is no point in solving this part. Okay, so maybe that was the error. We'll see. Again, some issue is there. I'll check and let you all know in the next class. Okay, I'll check this one. We'll solve other questions, then I'll check this one. So question number 6 is, due to an accident right before nationwide lockdown due to COVID-19 pandemic, an unknown amounts of BZC, that is benzyl chloride, is introduced into a small well-mixed pond that is used for drinking water reservoir. Working for the state water authority, you are asked to estimate how long, how much time it's going to take until the concentration is dropped to 1 microgram per liter. Because of the lockdown, it takes you 5 days until you are ready to make the first measurement. At this time, 5 days after the spill. Okay, so there is some initial concentration, and after 5 days only you are able to take the measurement. Okay, and after 5 days, the measurement is 5 microgram per liter, and 5 days after that measurement, the concentration is 23.6. So the thing is, at time and concentration. At 0, we don't know. Okay. At 5, we know it is 50. A second measurement 5 days later at 10, it is 23.5. We need to know the time when the concentration will be 1. This is the question. We need to find out these two values. Okay, this is for solving, this is the final answer, and this will be used for solving the problem. Try this question. Okay, we'll see the solution. So C5 is concentration of 5 days, that is 15. C10 is after 10 days. A well-mixed pond is example of batch reactor. Okay, we are not considering any incoming and outgoing flow for now. So C is equal to C naught e raised to power minus kT. So for 5 days, it is 50 is equal to C dot e raised to power minus 5k. And for second, it is 23.6 is C naught e raised to power minus 10k for 10 days. And by dividing, by cancelling C naught, we will get the value of k. And just put it in equation 1 and we will get the value of C naught. And simply just put it back in the equation of a batch reactor and we can get the value of T. Please note this down and let me know if anything you won't understand here. Note this down. We'll move forward to the next question.
Excuse me.
Yes.
So, see, this question completed or not?
Yeah, this question is completed. We needed
But
time, right? Hmm?
no need time. You can go. What is that? Now answer is 31 days, na?
Yes.
Yes, it's over. You can go further. Next question.
Yeah. No, I was giving you people time to, like, if in case of any doubt. I was
Yeah.
waiting.
If anyone
Yeah.
wait sometime then you can wait. No problem.
Yeah. Hmm. No
So
issue.
earlier question also that okay.
Okay. So this is the next question. So here you need to correct the, this is simple uh, multiple type question, multiple choice type question. You need to select the correct option. What is Bronsted-Lowry acid base theory? So I have already explained this question in the introduction part. We have discussed this. So please find out the answer and you write the answer in the chat box. Please write the answer in the chat box. Okay. So option number B and C are correct. Why D is not correct? Here, The answer you gave is there is D also, and D is for Lewis acid and base. Okay, it is not for Bronsted-Lowry acid base. Okay, so that is why option B and C are correct. First, it is applicable to only aqueous solution, and the compounds which are capable of donating a proton are called Bronsted acid. Okay, this non-bonding electron pair is only for the Lewis acid base concept. Okay, so option B and C are correct. So this is question number 8. A particular industry needs fluoride ion in the solution for chemical production. The source of fluoride ion available in the market is hydrofluoric acid, HF. What is the ideal value of pH at which this industry must operate? I will tell you an interesting fact about hydrofluoric acid. All types of acid, HCl, H2SO4, everything is available in glass bottles. Okay, all types of acid except this hydrofluoric acid. It is available in plastic bottles, PET bottles. So why this happens? This hydrofluoric acid is so strong, it can melt anything, even glass, but it cannot melt plastic. So this is an interesting fact about hydrofluoric acid. If you put anything, it is going to completely dissolve it. Concrete, even concrete, ceramic, anything in the world except plastic. So what will be the ideal pH value at which the industry must operate? We know the pKa. So option B, because for formation of fluoride ion, pH should be more than pKa. Okay, then B is correct because what we need is fluoride, and HF will change to H plus, F minus. Okay, so pKa is 3.17. Okay, we are calculating Ka. We can make it into pKa by negative log of the Ka concentration. That will be H plus F minus, sorry, this will be 10 raised to power minus 3.17 HF. So if we want more fluoride, what should happen? If we want more fluoride, the pH should reduce because we want reaction to go into uh, we want more fluoride, so we want reaction to go into forward direction. Okay, for moving the reaction to forward direction, these values should reduce. So what will we want H to reduce? So when H will reduce, what will happen? There will be increase in pH. If H will reduce, then OH will increase. When OH will increase, there will be increase in pH. So that is what we want. So that is why value more than pKa will give us more F negative. That is fluoride ion. The next question number 9, is acidic acid dissociates in water as below. So PHAC, that is acetic acid, it is dissociating and forming H plus and acetate ion. So we have this pKa value which is 4.76. The concentration of conjugate base, what is conjugate base here? You can answer in the chat box. And conjugate acid present after dissociation is, this is 10 raised to power minus 4.6. Okay, 10 raised to power. It is not minus here, it will be minus 4.6 here. It is raised in power. And 10 raised to power minus 2.8 mole per liter. Calculate the pH of the water solution using the Henderson-Hasselbalch equation. I hope you remembered that. I explained in the introduction itself. pH is equal to pKa and rest of the values. Please solve this question. You can answer in the chat box. Conjugate bases and conjugate acid. What will be those compounds? So this is the correct answer. pH is equal to pKa plus log conjugate acid divided by a conjugate base divided by conjugate acid. Okay. So just by putting it in the values, we'll get the correct answer. So pH is equal to 2.96. Please match this with yours. So conjugate base divided by conjugate acid. Then we'll move forward to the last question of the session. So this is the last question of the session. Which of the following acid is strongest at pH 8? HCl, HOBr, HCN, or this C6H5OH? Which will be the strongest acid at pH 8? We know the pKa values of all of them. Which will produce more H plus ion? Which is going to produce more H plus ion at pH 8? This is very interesting question. Okay. So HOCl will have more, that is hypochlorous acid will have more H plus than any other compound since pH is greater than pKa. For other compounds, for other pH is less than pKa, so that is why it will produce less H plus ion. But HOCl will have more, it is having pH more than pKa, so it will produce more H plus, and more the H plus, stronger the acid. Okay. And at some other pH, the other acid can be stronger. It's not like that HCl will be stronger all the time. At some other pH, other acid can be stronger. So pH does not solely decide if the compound is completely acidic or basic. This is just one concept that pH greater than 7 is considered basic and less than that acidic. Because in our labs, we have seen those compounds having pH 3. But even if you will touch it, nothing will happen. But H2SO4 and all at pH 5, you will burn your fingers. Okay? So pH is not a true identity of something is acid or basic. There are various different concepts. So that is all for today. Thank you, everyone.
Excuse me,
Ah, yes.
today's session is over.
Yes. So I'll
Uh,
try to explain both the methods to solve the question. So I think that will be
okay,
better. One
okay,
can pick
okay.
the easier method. Mhm.
Sure, sure. Next week, so
Yeah.
I'll join with you. Okay. Next
Yes,
session,
yes.
I'll join. Okay.
Yes, yes, yes. Oh, okay.
Bye.
And
Okay.
thank you for the feedback.
Okay. Okay. Bye.
Okay. Thank you so much.